Hello everyone. In this video, we are going to talk about the effect of zeros of a transfer function. So if you watched my videos on controls, here and there I talked about the effect of zeros when I talked about the root locus and the frequency response and so on, or maybe PID control, but this question came up in my controls course, and one of my students said when I was talking about the characteristic equation and that poles of the system will determine the stability of it, right? Whether they are on the left side, right side, or on the imaginary axis. And he said, what about the zeros? What would be the effect of zeros on the stability or any other thing in the system? And so I decided to kind of summarize the effects of the zeros of transfer function here in one video if you are curious about it. Because all we talk about most of the time is where are the poles of the system? Where do we move the poles of the system to change the behavior of the system? But what about the zeros? So let's take a look. So as I said, the zeros of the transfer function do not directly determine the stability of the system, okay? The stability is directly determined by the poles of the system. Now, they have some effects, like what? So before I show you the effects, here is an example that if the zero is on the right side of the imaginary axis, the system could still be stable, right? So here I have a system with the poles at -1 plus minus j, but the zero is at +3, so it's on the right side. And here you can see the step response of the system that still is converging to some steady state value. It's not growing, and the system shows stable behavior, although the zero is on the right hand side. And here is the code for that, right? So you can see that this is the numerator, that's the denominator, the system. I showed the step response, and this is the step response that you see. This is stable, okay? So now let's look at the actual effects of zeros. Now that they cannot do direct impact on stability, what can they do? The first one is they can indirectly affect the stability. How? By shifting the root locus. So what is root locus? I have a couple of videos in this controls playlist where I showed you how to create root locus and then also how to design a compensator based on root locus. But basically, root locus is the location of the closed loop poles if you have some gain in the system that you can change. For instance, if you consider this control system, you know that the closed loop transfer function is g over 1 plus gh, and so the poles of the system are the roots of this characteristic polynomial, so we have to set it equal to 0. Now, if either g or h has this tunable gain k, and then the product of gh, which we call open loop transfer function, can be written like this. So it has a bunch of zeros, 1 to m, and a bunch of poles, 1 to n. Then we draw the root locus for this open loop transfer function, because here we can see that g times h should be equal to -1, which means the magnitude of it should be 1, and the angle of it, if you treat it like a complex number, should be 180 degrees. Therefore, based on changing this k, we can show the roots of this open loop closed loop transfer function, or where gh equals -1, and you're going to get something like this. For instance, here you have 3 poles and 1 0. Now, what is the effect of the zeros in g or h on this guy? We're going to see, but the k here, first of all, you have n branches of root locus, and n is the number of the poles here. So here, let's say the system was order 3, so there are 3 branches. Each branch starts at a pole of one of these p's and ends at one of these zeros. Now, if you have 1 0, then the 2 other zeros are 2 imaginary ones at infinity. So these 2 branches go to infinity, and this branch starts at the pole and ends at the 0. And the gain at these poles is approximately 0, very small. And as you go to infinity, then the gain gets bigger and bigger. Now, of course, if your root locus is such that it moves to the right half plane, that means per some of these gains, the closed loop poles of the system can be in the right hand side, and that means the system could go unstable. Okay, so you don't really want your root locus to these branches to move to the right side. It's always good to keep them in the left side, right? So now you might say, what's the effect of these zeros? So the effect of these zeros can be seen in several places. One is, of course, first of all, if you add zeros on the left half plane, so if you add another zero here, what happens? Remember, your branches, as I said, start at the pole, end at the zero. So because you end at the zero, by adding one more zero here, now you are forcing one of those branches, instead of just keep going, one of them has to come and end here. And since this guy is on the left side, your branches will shift left. So your root locus will shift left if you add zeros on the left hand side. And because of that, now more of the poles of the system for different gains will end up on the left side, which means the system will have improved stability. Okay, so this is your effect on the left hand side poles. On the other hand, if your zero end up on the right hand side, now because everything should end at the zeros, one of your branches should come here, and clearly that branch will end up in the right hand side. So your and that zero, which is on the right hand side, by the way, we're going to call it a non-minimum phase zero. Why? I'll show you in a second. And that will destabilize the system and degrade the performance, as I'll show you, as I said. So clearly you see, by adding zeros on the left hand side, you make the system more stable, on the right hand side less stable. Another way you can look at the effect of it is by these asymptotes, the angle of them, and by the location of their intersect. So in this case here, the intercept and the location is where, for instance, the intercept is maybe here or somewhere here, and then the angle of them is 90 degrees in this case, right? Because you have 3 poles and 1 0. So this is 3, this is 1. So your angle, in this case, an integer number, the first one could be 0. So your angle is going to be 180 divided by 2. So it's going to be plus minus 90 degrees, as you can see. And so these branches will never end up on the right hand side because the angles are 90 degrees, right? Now, if I get rid of one of these zeros, what happens? So if I get rid of this, what happens? Now this becomes 3 minus 0, so you end up with plus minus 60 degrees. So now your basically your asymptote angles will be 60 degrees, and so they're going to be like this. And these branches, instead of going straight up, now these branches are going to go like this. And there we go. Now you make them end up in the right hand side, and so now the poles will be on the right hand side, so the system becomes less stable by getting rid of that zero. By adding that zero, you make these angles bigger, so these branches more stay on the left half plane instead of ending up in the right half plane. Okay, so you see it affects the angles, and also the location of these intersects. This point here, S, is also determined by the number of zeros as well, right? So clearly, so here you saw that if I make the number of zeros more on the left hand side, the whole denominator drops. That means the whole angle goes up, and the angle bigger is better. Now, what about the location? So here, if I make more zeros on the left hand side, then the denominator drops, but also you have this guy here, which is important. Now, if the zeros are on the left hand side, then some of them is going to be a negative number. Okay, some of them is going to be a negative number. Negative of that is going to make it a bigger positive number, right? And so you see the effect is because of two things, m and zeros. So for instance, I had a system where the poles were at -1 and -2, right? And no zeros. And so the intersection point was -2/3, -3/2. Now to this system, I add a zero maybe to their left side. So now I add something like this, 1 0 at -8, for instance. And now I have 1 0. So if you look here, now you're looking at basically 5 over 1, which is positive 5. So now the intersection comes here, and that is not good. So you see, with the intersection of the asymptotes, it's not really clear to explain it. It depends on where these zeros are. But in terms of the angle, you can see, and better than that, it's the fact that the branches end up at zeros, where the left hand plane zeros will shift it to the left, make it more stable, and the ones on the right make it less stable. Now, to demonstrate that for you here, I wrote this small code. So my first system has no zero. My second system, I add a zero on the left-hand side at -8. The next one, I add one at +8. And their denominators are all same third order. And then I show you the root Lucas of them using the command rLucas. So you see the difference for adding a zero on the left-hand side, adding a zero on the right-hand side, and the effect of that on stability. So let me run this for you. There we go. So look here. This is very interesting, right? So this is the original system with basically no zeros, right? Look at that. Clearly, you can see that these two branches will end up in the right side for some big k values. Now, if I add one at -8, look, there is no branch on the right-hand side for any k value. So this system is clearly more stable than that. But if I add it at +8, look what happens. This branch completely ends up, a big portion of it on the right-hand side, because the zero is here, as I explained to you. And clearly you see that this is less stable than that. This is more stable than that. So this shift of the root Lucas is something that is important, and you can understand it here. Okay, so we have seen the effect on root Lucas. What's the other effect? The other effect is on transient response. Well, of course, if you have the capability of moving the poles of the system to the left and right, those poles affect the transient response. So if you add a zero, one of the things you can see is they can create some initial dips or peaks, some ups and downs in, or overshoots and undershoots in the time response. Basically, they can accentuate or shape the form of the transient response, creating, as I said, overshoots or undershoots. As an example, if you have a second order system and you add a zero near origin, you can create what we call a peaking effect and make the system create more overshoot. Why? Because the energy that is temporarily stored in the system and then released in the beginning. So because of that energy stored in the system will show an overshoot here. So to show you an example, here we're going to see two systems. The first one that has no zero with this transfer function, and the second one we add a zero close to the origin at -0.1, and we're going to see their step response. So here the step responses are shown. And as you can see, the system that has a zero near origin, look at the overshoot of it, because the value should be about 0.5. Look at the percent overshoot that this guy has, right? So this should be, about 0.05. It goes close to 0.5, right? So it's a huge percent overshoot, while this guy, the overshoot only goes from 0.5 to like 0.65, okay? So you see the percent overshoot here is this number divided by that, while here is this number divided by this. Okay, so adding that will cause, of course, a big overshoot. And again, that one here, I guess I have the code for it. And you can see the code right over here, correct? So all I need is to close this and run that section for you. And you can see the effect of, there we go, adding no zero and adding a zero, as you can see over here, okay? Which you can see in a second order system. Another thing is adding a zero to the system can speed up the system response in the time domain, because a zero acts quite a bit like a high pass filter. Imagine your zero is at zero itself. Right? If the zero is at zero, then your term for it is simply s, and s is a derivative. Now, if the 0 is at -1, your numerator is s plus 1, although this one is not exactly derivative, but it acts similar to a derivative, right? So if I have this guy over something else, this is a high-pass filter, right? And the high-pass filter acts like a derivative, and derivatives will emphasize higher frequencies, high-pass filters, so they make a faster rise time. And that's, I guess you can see over here, again, if you want to look at it, the rise time is the time that it takes the output to reach the input for the first time. So if you look here, the rise time for this system, if I can zoom in, is basically a very short time, and in that case it's just this distance here, this time here, this is small time. That is the rise time. It took it from 0 to reach to the final level, but for this guy it's this much. It takes that much time to reach to that. Or if you look at the peak time again, this is the peak time for the original system. With the one with the 0, and this is for the one without 0, the original one. Yes, so you see it clearly makes your rise time or peak time to get smaller at the cost of overshoot, because you can never make a system that reaches the final value very fast, of course, will overshoot it more. Yes, so adding a 0 will make the percent overshoot to go higher, but makes the rise time and the peak time to go down. Okay, so, and especially if the 0 is close to origin. So that you can see over here. What about in the frequency domain? So we kind of barely mentioned this non-zero, non-minimum phase zeros. Let's talk a little bit about it. So if the zeros are on the right side of the right half plane, we call them non-minimum phase zeros. Although they don't directly make the system unstable, indirectly do, but they also cause some kind of effects on the transient response. Like what? One of them is called inverse response. What is this? So initially, your output will move in the opposite direction of the input before it moves in the direction of input. Okay, because the zeros cancel some parts of the input effect early on, delaying the actual expected response. So this causes the system to, of course, act a little bit slower, because first it goes in the opposite direction, then moves in the direction of the input, and so slows down the system. And here you can see one example with a minimum phase 0 and a non-minimum phase 1. So here the 0 is at +2, here is at -2, the same denominator. First of all, why do we call them non-minimum phase? Because if you draw Bode diagram for them, magnitude and phase in the frequency domain, you see although both systems share the same magnitude, but the phase of the system with a 0 on the right-hand side, or a non-minimum phase 0, the phase of it is much bigger than the other one, right? So you see the blue system has a much bigger phase than the red system. So that's what we call a non-minimum phase. But if you look at their step responses also, that's very interesting. So here, the system that has the 0 on the left-hand side, the system with the minimum phase, look at the response of it. The final value it should reach at is like 0.6364, and it starts at 0 and immediately moves in the direction of that and tries to reach it. But the blue system should reach this value of -6.3 or something. And although initially it's at 0 and it should start going down in that direction and trying to reach it, but look what happens. You see that initially, instead of going directly from 0 to that negative number, first it goes up, then goes down. So this inverse basically response that you will see will cause the settling time of the system to be bigger here compared to here, and that is absolutely not a good thing. Now, next thing in the frequency domain, based on what you know from Bode plots, is if I have a 0 like this, then you know that the magnitude and the phase for a 0 like that is basically, this is the magnitude, this is the phase, And if you plot them, you see this is the gain, this is the phase, right? And clearly you see that the gain of a 0 is positive, right? And also the phase of it is positive. So basically you can say that adding a 0 will add to the gain of the system at any frequency, and it will also cause a phase lead, which you can see here. So it can boost gains at desired frequencies, and also it can introduce phase lead as long as that 0 is in the left half plane. Okay, if it's in the left half plane, then you get exactly what you want. So extra phase lead, as you know, can improve the phase margin of the system and potentially enhance the stability like we talked in the past. But if the 0 goes to the right hand plane, then you're going to have phase lag and you're going to get worse phase margin and longer delays and worse stability. So you definitely want to have it on the left hand side to make your system faster, to make your system more stable, of course at the cost of more overshoot, and increase your gain, increase your phase margin, and so on. And finally, we have pole 0 cancellation. So if you place a 0 to cancel a pole, then you can do a pole 0 cancellation. So when 1 0 is exactly equal to 1 pole, for instance, you can cancel the slow poles of the system, so you can make the system faster. So for instance, let's say your transfer function is something like this: 1 over s plus 0.2 times s plus 5, right? Or this guy could be s squared plus something. Now, you know this is a slow exponential, correct? So one thing you can do, maybe let's say add multiplied by something else. One thing you can do is say, hey, look, this guy is causing the system to act very slowly. These two are exponential of negative 5t and negative 60. They go to 0 fast, but this one does not. So if I add another 0 like this to the system, then these two would cancel each other and the resulting system is going to be faster. So if a 0 can cancel a slow pole, right, then you can improve this speed of the system. The danger of this cancellation is when the 0 and pole, you think they are canceling each other, and that pole is an unstable pole. So let's say here you have something like this. This guy is negative 0.2. So that guy is on the right hand side and the system is unstable. And you say, well, no worries, I can make the system stable by simply adding a 0 like this, and then these two would cancel each other. So by just adding an unstable 0 to a system that has unstable pole and pole 0 cancellation, I get the system to be stable. The only problem is that cancellation happens if and only if these two numbers are exactly perfectly equal. But many times in a physical system, these numbers, they do depend on the system parameters. For instance, if it's a mass spring damper system, these numbers could depend on the mass or spring or damper or their products or anything. Now, if you don't know the values of mass, spring, or damper very, very accurately, there is a small imperfection in it. Guess what? You think this number, based on the MCK, this number should be 0.2, right? Negative 0.2, and therefore you add a 0, add negative 0.2 here. But in reality, this number that comes from system parameters was not exactly 0.2, it was like 0.199, okay? It's very small difference. Now, these two will not cancel each other. They will not cancel each other, and although you think the system is going to be stable, it's not going to be stable. So to show you that, here I have this system which has the poles at negative 0.99 and negative 2. And I thought the pole should be at negative 2 and negative 1, right? So I thought this is like S plus 2 times S minus 1. Actually, this should be positive 99. Okay. And for that, I added S minus 1 to the numerator to cancel that. But in reality, that point was S minus 0.99, it was not exactly at 2. So although these two are very close, they won't cancel each other. And look at the step response of the system. Look how big it becomes, and this is clearly an unstable system. And this is that pole zero cancellation, the same thing I showed you, and it should be positive 99. And if I run this, you can clearly see that the response is unstable, as you can see. Okay, so you can have code like this and figure out the effects of zero on the response of a system, whether it's a indirect effect on stability, whether it's the transient response, overshoot, the rise time, peak time, whether it's the effect on the phase of the system, right? The phase margin, whether the effect on the gain of the system, right? Whether it shows, it creates an inverse response or not, whether it can cancel a slow pole or apparently cancel an unstable pole, but it doesn't, and your system still goes unstable. So these are the summary of effects of zero of transfer functions. Hopefully the video was useful to you. I'll see you in the next lecture. Thank you.